Now let's start our discussion on the first law that is applied on flow processes. Now before we move on to the more details of this topic, let's start by understanding what is a control volume. Now if you have any process or you have a system that is undergoing a process, the first law is written as Q is equal to delta E plus W. Now sometimes this delta E is also written as delta U. So it is one and the same thing. Alright. Now the value that is E, or you can take U for instance, this represents all forms of energy that is stored in the system. This is the representation of all forms of energy stored in the system. Okay. Now what kind of energies are these? So we'll take care of, or we'll talk about a pure substance in this case. So if you have a pure substance, alright, then the pure substance, the energy that we are concerned about is, let me put the energy as E only. So you would have EK plus EP plus U. Now in this equation you have the energies that are stored in a pure substance, and EK is the kinetic energy, alright, EP is the potential energy, and U is the residual energy that is there in the molecular structure of the substance. It is the residual energy in the molecular structure of the substance. Alright, now if I apply this onto the first law, so I would get Q is equal to delta EK plus delta EP plus delta U plus W. So this is what I will get. So this is the sum of all energies in the system, that is delta E. Alright. So which we call the internal energy of the system. Now let us name this equation as equation 1. Alright, and this equation is valid for, you can say, an open system. So this is valid for an open system where the mass can flow in and out of a system. And let us say we have a system of a particular mass of substance and it is free to move from one place to the other place. And let us take the case of a steam turbine. So this is the turbine that is handling steam, which is the fluid in motion. Okay, so let us consider the steam turbine in which steam enters at high pressure. So this is where the steam would enter. This is the inlet point. So this is in. Okay. And it does its work on the rotor. So you get some work output. And the rotor is in the turbine. So it turns the rotor. The output shaft will also turn and you would get some work output. And then the exhaust steam or the condensate or the, you can say, the spent steam energy is then, led out of the turbine with the help of an exhaust pipe. So this is the exhaust pipe through which the used steam, it leaves the turbine casing. Now we will consider the, you can or you can say a certain mass of steam. Okay, it can be 1 kg, it can be 2 kg, or it can be any number of kgs. So this mass of steam is considered our thermodynamic system. So the system that we are analyzing over here is a certain mass of steam only. Alright, and to analyze the expansion process in the turbine, the moving system. Why we call it a moving system? Because steam is flowing inside this turbine. Alright, so in order to analyze the expansion process in turbine, the moving system is to be followed as it travels through the turbine. So as the steam enters and flows over the rotors and then flows out of the exhaust pipe. So in this flow we will track the motion, or we will track the movement of the steam or the moving fluid or the moving system, and we will also take into account the work and heat interactions all the way through. Okay, so this is how we would analyze this certain mass of steam, that is our thermodynamic system, by tracking or by taking into consideration all the movements and the work and heat interactions. And this method of analysis is similar to the Lagrange's method of fluid mechanics, in which Lagrange's method of fluid mechanics. Now, so what we are doing in this case, we are actually considering the steam that is flowing like this in the rotor and then coming out. So this moving fluid is basically my system. Okay. Now this approach of taking a thermodynamic system with a, you can say, a moving fluid, this is quite valid, but there is a different convenient approach as well. Now what we do, instead of concentrating attention upon a certain quantity of fluid, so this is the certain quantity of fluid which we were actually analyzing before. So now we don't do it. So instead of concentrating on a certain quantity of fluid which constitutes of a moving system, we pay attention to a certain fixed region in space. So I'll write these words down. So we pay attention to a certain fixed region in space. Alright, so this is what we do. So this is the system that we now consider. Okay, and this certain fixed region in space is what we call the control volume. The control volume. Okay, and through this control volume, the moving fluid flows, or the fluid flows. The moving fluid flows. So instead of only paying attention to this moving fluid as our system, we take a fixed region in space. It is not moving, but through this fixed region we have our fluid moving, and we call this fixed region as our system or our control volume. Okay. So if you look at this particular diagram, this complete volume or this complete region through which the steam is flowing is called the control volume. Okay, and this particular broken line, this line, this is called the control surface. So this is the control surface. Alright. Now a very important point that you should remember for this particular analysis or for this concept is that it may be noted that while the system boundary, it usually changes shape, position and orientation, the control volume boundary, it remains fixed and unchanged or unaltered. So you can say that the system boundary this is fixed and unaltered or unchanged. Alright, but sorry, no, this is not the case in this. The system boundary, it may change. It is not fixed, but it may change. Alright, but the control volume boundary, it is fixed and unaltered. So these 2 points are very, very important to distinguish between the two concepts. Is that if you take the first concept and consider the certain quantity of fluid as your system, then the system boundary may change in shape, it may change in position, and it may change in orientation with respect to the observer. But in case of the control volume analysis, the boundary remains fixed and unaltered. Okay, so this is a very, very important concept to understand. Now, this is the beginning of the topic of the first law application to flow processes, and the very first concept that you need to understand is that of the control volume, and that we have just discussed. Now, after this video, now we'll talk in the next video about steady flow processes, and we'll specifically talk about the mass balance and the energy balance in a simple steady flow process.